So guys, in this example, A is a set containing -1, 2, 4, 5, 6 and R is a relation on A defined as x or y if and only if max x comma y belongs to 4 comma 5. Then we have to test for reflexive, symmetric and transitive. So what is the meaning? R is a relation on A means x is also belonging to A, y is also belonging to this set A, okay, containing -1, 4, 5, 6. And then what is the meaning of this line, which is max x comma y belongs to 4 comma 5? Once we understand this, that will gives us the way, provide the way of solving it further. So understanding it is the approach, and that's the hint to this. So max x comma y belongs to 4 comma 5 is means what? So first of all, max, it will be either 4 or 6. Any one will come or both will come. Greater than 4, 5 won't come. Means 6 won't come at any cost. 6 is won't be coming, right? 4 will come or 5 will come or both will come in all ordered pair, because that's the maximum value. The maximum value in any ordered pair can be 4 or 5. That is the meaning. So the any ordered pair can be 4 comma 1, 2 comma 5, 4 comma 5. Okay, at least one would be present out of 4 and 5. So if we try to write it, we will start with 4. So we will start with 4, then all other values lesser than 4 we will write, which are -1, 2, 4. This is another case when 5 is also added. So again 4 comma 5 will also be there. So if 4 is in A, so other values would be -1, 2. Okay, because 4 comma 4 is already included. Similarly 5 in the last we will take. So other values would be -1, 2, 4 we have already taken, 5 comma 5 we will take, then 5 first in the first place. So other values -1, 2 we will take. So that all these are the all ordered pairs which constitute the definition max of xy is 4 comma 5. So if you count this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there are 12 values. So now we will check for reflexive, right? So for reflexive, 6 comma 6 is not there. So directly we can say that it's not reflexive. For symmetricity, again we will check, see if 2 comma 5 is there, 5 comma 2 is there, -1, 4, 4 comma -1 is there, 2 comma 4, 4 comma 2 is there, 4, 5, 5, 5, 5, 4. So -1, 5, 5, -1. So yes, it is symmetric, guys. Transitivity, we will again check. Now if you see -1, 4 and 4 -1, so A, B, B, A in this case, B, C, okay, or sorry, A, B, these two are there, then definitely -1, -1 should be there for transitivity, which is not present. So guys, this is not a transitive relation, okay. So it is reflexive but not symmetric and transitive, guys. Let's see an example from mains 2024. Let a relation R defined on n with natural number x1, y1 are x2, y2 if and only if x1 is less than equal to x2 or y1 is less than equal to y2. Defined on n means the constituent, the elements of each ordered pair here, x1, y1, x2, y2 is, they are all natural numbers. Now the first statement says that R is reflexive and not symmetric and second statement says is R is transitive, then the true option. A, which is second, B is third, B is first option, C is both, D is neither. Okay. So how we can attempt this, guys? So what should be the approach to this problem, guys? Now here x1 less than x2 or y1 less than equal to y2 means what, guys? Any one or both if it is satisfying, any one if this is true, this is not true, okay, or this is true, this is not true, or guys both are true, okay. In that case it will be satisfied, guys. Okay, if both are true it will be correct. So that is the meaning. So how we will approach this, guys? So we will see some basic rules of inequality. We will try to use some examples, counter examples to verify, and if not, then we will try to prove it. Okay, so we will using examples. We will try, and the properties of basic inequality we will try to verify. We will take examples taking into consideration when the first statement is not true, however second is true, because or is given, so any one is true or both are true is valid. And then we will take some example when the first one x1 is less than equal to x2 is true, but the second one is not true. And we will also take examples x1 less than equal to x2 and y1 is less than equal to y2. So that way we will try to verify, and using inequality we can prove also. So we will start with the reflexive property where x1, y1, x2, y2 they are belonging to natural number. Okay, so reflexive property, so we will substitute x2 as x1, y2 as y1, so that both the element are same. x1 y1 here also x1 y1. So this becomes x1 less than equal to x1, which is true, y1 is less than equal to y1, both are true, and if any one is true then also it is true. So this whole thing is true, so it is reflexive, we can say. Okay, now for symmetric, so we will, if this is true, x1 y1 x2 y2, okay, if this is true means x1 less than equal to x2 or y1 is less than equal to y2 or both is true, then if we interchange x1 y1, if we interchange x1 y1, so now we will get x2 y2 are x1 y1. So here also now it becomes x2 less than equal to x1 or y2 less than equal to y1. So can we think of some example for which this won't hold? So as you can see, if you take 1 2 3 7, so 1 less than equal to 3, 2 less than equal to 7, this is both are true, so this is true. Now if we interchange it, so 3 7 are 1 2, in that case now 3 won't be lesser than 1, 7 won't be lesser than or equal to 2. So this example or counter example clearly refutes that it is symmetric, so no need to prove it. Now in the similar way for transitive as well, if we assume these two x1 y1 x2 y2 and x2 y2 x3 y3 to be, this is true and this is also true, so in that case we have to prove these two, like x1 y1 and x3 y3, which I have written here. So this we have to prove, we have to check whether this is true or not. Okay, so we will try to take a counter example if it refutes the last one. Okay, x1 y1 x3 y3, so we will choose x1 y1 x2 y2 and x3 y3 like this. guys. We will choose x1 y1 as 1 7, x2 y2 as 3 3, and x3 y3 as 0 5. So as you can see here, in the first x1 y1 are x2 y2, 1 less than equal to 3 is true. However, 7 is not less than equal to 3. So first is true. So this whole thing is true because at least only one or it is given. So if at least one is true, it will be true. Now similarly, x2 y2, we will prove x2 y2, x3 y3. So 3 and 0, so they are not less than equal to. So this is wrong. But if you take 3 and 5, y2 and y3 as 3 and 5, this is again correct, guys. Okay. So these two we have taken. Now we will check for what, guys? In order for this to be transitive, we will check for x1 y1 and x3 y3. So which I have substituted 1705 here. So 17, so 1 less than equal to 0 it becomes, guys. So 1 less than equal to 0 is not correct. 7 less than equal to not 5 is also means 7 is not less than equal to 5, and 1 is not less than equal to 0. So neither of them are correct. So this is an example, a counter example that we thought of, which refutes this to be transitive. So this is of course not transitive. So from the options, if we check, the first is correct. Okay, so first is correct. So first we will take, although this question is done even before doing transitive, because if you see, because but both option was also there, so we had to check transitive also. So yes, we have to check transitive. So we checked for transitive, which is R is not transitive, so second is false. So only correct is first option. That is our answer, guys. Okay. Let's take a question from mains 2024. Okay, this is a question which goes like this, guys. Let us set A 2, 3, 6, 8, 9, 11 and set B 1, 4, 5, 10, 15. Let R be a relation on A cross B, that is AB comma CD belong to A cross B whole square, such that AB ordered R, CD ordered, if and only if 3AD minus 7BC is an even integer. Then R is, this is single correct, reflexive but not symmetric, transitive but not symmetric, reflexive and symmetric but not transitive, equivalence relation, guys. So this is the question. Let's try to understand the meaning of this question, guys. Okay, now two sets A and B are given. Now if we multiply them, the Cartesian product can be found by multiplying A into B, so that A cross B can be formed. So A cross B into A cross B will generate one ordered pair AB. So if A cross B is again multiplied to A cross B, we will get element like this, ordered pair of two ordered pair AB and CD. So obviously AB would be what? AB, definitely the first elements AB would be AC would be element of set A, and B and D would be element of set B. That is well understood. Now they're defining it as A, B, C, D. This is an element, will be a part of this R, that is the relation, if and only if we substitute A, B, C, D in this expression 3AD minus 7BC, and if it gives an even integer, then it would be called as an a part of this R. Then R we need to calculate reflexive, symmetric, transitive, and all we need to check. So how we can approach this, guys? So as you can see, the value of 3AD minus 7BC, this 3AD minus 7BC, depending on A and B and C and D, which depends on A set A and set B, which contains even and odd numbers. So it's all about the concept of even odd multiplication and addition subtraction, because then only we can get even number. Like the concept here is the basic thing, like even minus even and odd minus odd, both are even. Product of even, in if at least one is even, then the product is even. Only it is odd when both the numbers are odd. Odd into odd is only odd. So either we try to prove it or we take counter example. We will take counter, because if you try to prove for reflexive, in which we will equate reflexive and symmetric also, in which we will interchange, reflexive and symmetric would be done easily. We need to first take counter example which does not prove transitive, else if we can prove, later we can prove to be transitive if we cannot prove it using any counter example. So proceeding one by one with first proving reflective, then symmetric, and then finally transitive. So reflective and symmetric, as I said, it would be done easily. So in the solution part, reflexive, A, B, C, D. So C, D is also A, B. So A, B, R, A, B. So in place of C, we will put what, and in place of D, we will put what. So guys, again, in place of C, we will put A, in place of D, we will put B. So 3AB minus 7AB, it would be what, guys? It would be minus 4AB. A, for irrespective of AB, since 4 is multiplied, it is definitely even, whether A is odd, even, or whatever. So reflexive is proved. Now for symmetric, again A, B, C, D, we will interchange, it becomes C, D, A, B. So if this is even, okay, if this is an element, so this is even, okay. So we have to prove that 3C minus 7DA to be even also. So we will do some manipulation. We will write 3CB as 7BC minus 4BC and minus 7DA as minus 3 minus 4AD. Okay, so like it would be like this. Minus 4 will take common, BC plus AD. 7BC minus 3AD. If you see from here, it is 7AD minus 7BC. The same term came minus times. So even if it is minus times, it will still, this will still be called as even. And since this is 4 here, it would be again even. Even minus even is even. So symmetric is proved, guys. Now about transitivity, in order to prove transitive, so what is, let's see what transitive means actually. So if you take A, B, C, D, C, D, E, F, so we have to prove for A, B, E, F to be what? To be even. If these two are even, so we have to prove this to be even also. Okay. So let's try to counter prove this. Like if you take some case, and if you can prove that this is not correct for some case, then definitely it won't be transitive, because in order to prove it to be transitive, we need to take so many cases, guys. But in order to prove not to be transitive, we can either take a counter example, simple example we can think, or if we take a case when if it is odd, we will take only one case. where first term is odd, second is even. There can be another case also. So what we are doing, we are trying to disprove it by assuming it to be odd. At the first term, 3af is odd, 7b is even. We can also prove it by even minus odd, but this is sufficient. Okay, if one thing is proved, disproves, the other things won't be required. So odd into odd means odd into odd, even means odd into even. So it means what, guys? It means a is odd, and guys, here, so a is 3af, so a is odd here, and b is odd here. Similarly, e is even, f is odd. So it is like this, guys. ab is taken to be, if ab is taken to be odd, ef taken to be even and odd, that we will write here odd for ab, here also odd for a and b, here also ef even, f for even, so here also f for odd and e for even. Now we need to prove this. We have to take c and d, choose c and d in such a way that this becomes even and this becomes even. So what should be c and d? Odd, even, even, odd, even, even. What kind of possibility we can take? If you think a bit, and if you take c as even and d as even, now even if you think that way, like from the question, from this we can deduce also, like here 3ad is we need to choose d such that and c such that this is even. So if you choose d to be even and c to be even, then only it is possible, because if you take d or c any one to be odd, then it would be odd minus even kind of case, so it would be odd only. So d and c, in this case it has to be even only. So here also even, so here also I will write as even and even. So as you can see, both are even, so this even and this even, they came as a natural consequence. So we proved that if we take this as odd, still we can take these two as even. So this is not equal. See, if we have taken a b c d c d e f, so a b e f is not even, is equal to odd means this is not even. So we disproved this, that it is not transitive. For example, if you take, it is like this scenario, this is what we discussed. We know the value of b and a, that we will substitute here in place of a b c d and e f in the next step, taking into account whether they are odd or even. Okay, this we will take into account, and we will assign values from set a and b like this. So b and a, we have assigned values. a b we have assigned 9 5, c d 2 4, against c d 2 4 to e f 4 5. So a b to e f 4 5. So as you can see here, this I will calculate 9 5 3 9 5 minus 7 5 into 4. This is 7 3 into 9 into 5 30 135 into 5 4 are 20 140 minus 5, which is odd. So it disproves this. So this is what, guys? This is not transitive. So this is not transitive. So which option we will take, guys? This is symmetric, this is reflexive. Okay, so reflexive and symmetric, but it is not transitive. Answer is option number C, guys. Now let's see, what do we mean by this equivalence relation. So far we have seen reflexive, symmetric, transitive. Equivalence relation, it's a relation, is said to be equivalence. Equivalence take care of if other three are okay, all are conditions are met for symmetric, reflexive, and transitive, then it is equivalence. That is the meaning. Like a relation is said to be equivalence if and only if it is reflexive, symmetric, as well as transitive. Okay, so if all these three are met, we say that it is what, guys? It is equivalence. Okay, so let's take some example on this, guys. So we can also say that a relation is if it is reflexive, symmetric, as well as transitive and is there, then we can say that the relation is RE. That is, E stands for equivalence. Some examples of reflexive relation, guys, is like if A is given to be 5, 7, minus 4, then this R1, okay, this is an example of reflexive relation. As you can see here, 5, 7, minus 4, so 5, 5, 7, 7 and minus 4 must be there. So as you can see here, 5, 5, 7, 7 and minus 4 is there. So this R reflexive condition is met, guys. Okay, this condition is met. Now, as you can see here, if 5, 7 is there, for symmetricity we need to check if AB is there, then BA should also be there. So it is also there. So we can say that the condition of symmetric is also there. Now, if 5, 7 and 7, 5 both are there, then 5, 5 should be there using the condition for transitivity. So as you can see here, that is also being met. Okay, so all the three conditions are met. So this is what? This is an equivalence relation. Another example of an equivalence relation pertaining to this 5, 7, minus 4. Okay, A to A it is defined. R1, A is 5, 7, minus 4. So again, same thing, 5, 5, 5, 5, 7, 7 and minus 4 is there. So the relation reflexive, that is met. Again, 5 minus 4 is given. So AB is given, BA should be there for symmetricity. So as you can see, 5 minus 4, 4, 7, minus 4, 7 is also given. Okay, 5, 7, minus 4, 5 minus 4. So guys, this is just a minute. This 5 minus 4, then minus 4, 5 if it has to be there. So yes, okay. And again 5 minus 4 and minus 4, 7 is given. So 7 comma minus 4 is, I have also added here to make it what, guys? Equivalence, to make it symmetric. First of all, equivalence we will see. Okay, and then here 7 minus 4 is met. Minus 4, 5, 5 minus 1. Now we will see for, so 5, 7. So I will also add 7 comma 5 here. Now symmetricity is met. Now minus 4, 5 and 5 minus 4, we are testing for transitivity, means AB and BC is there, then we should also have AC. 7 minus 4, 7 is there. 7, 5, 5 minus 4, 7 comma minus 4 is there. Guys, see this. This is AB BC, okay, CA, AC, okay, it is there, minus 4 7 and 7 minus 4, so it is there, 5 7 7 5, so 5 5 7, everything is there, minus 4 5 5 7, so minus 4 7 should be there here also, as you can see, minus 4 5 5 7, so minus 4 7 is also there. So this is another example of a transitivity is met, so we can say that it is an equivalence relation. Okay, now in this example, okay, is this equivalence relation? That's the question here. So guys, as you can see here, PP QQ is there. So the condition of the relation being reflexive is met. What about symmetricity, symmetric relation? So as we can see here, PQ is there, so it also requires QP to be an element, but QP is not present here. So the symmetric, it's not a symmetric relation. So any one thing, if it fails, it won't be, we won't test for transitivity, okay? And if one relation it fails to be, then equivalence answer won't be equivalence, okay? It won't be an equivalence relation. So now let's take an example. If A is P comma Q, find minimum number of elements that can be added in this relation R Q comma Q to make it reflexive, symmetric, transitive, and finally equivalence relation. How we can attempt this, guys? So the hint should be what, guys? So in order to ensure that it is reflexive, we need to have all the AAs, number of elements, whatever are there, that many ordered pairs of the type AA should be there. So that we have, even if it is missing, then we have to put remaining AAs. Okay, and let's say the extra remaining AAs that we put, we name it, let it is N1. So N1 is number of elements that we need to add. For symmetricity, yes, symmetricity, you need to check AB, then you have to search for BA. If not, then you have to put BA. So that element you need to add. Now, if only A is given, then no need, we know there no need to add. So N2, we need, N2 is number of elements for symmetricity. That the minimum number we are going for, okay? Because more numbers can be added apart from minimum, still it can be equivalence. That's why the question is asking for minimum, and that is the meaning of minimum number of elements to be added. Transitive, again, we if AA is there, then we don't add anything. But yes, if AB, you think you search for AB. So sorry, if you see AB, then you seek for something which starts with B. Let's say you got BC, then you should seek for AC. If not, if AC is not, then you need to add that. So that element you need to add, that many elements, let's say it is N3. So minimum number of elements is the sum total of number of reflexive, symmetric, and number of transitive elements. Okay, so moving with the same, proceeding with the same concept, same approach, the solution goes like this, guys. So for reflexive, as I said, we have to put remaining AAs. So PQ, but only Q comma Q was there. So we need to put one more what? Yes, P comma P we need to add. So one element we are adding, so N1 is 1. Symmetricity, now if AB, we need to add BA if it is not there. A, then no problem. So as you can see here, in this q comma q only was there. What we need to add, since there is no such element of the form a comma b, only q comma q was there, so no need to add anything. Q comma q is itself sufficient. So n2, nothing we need to add, it is 0 only. For transitivity, guys, if AA, then don't add. But if you think of AB, then you think of B starting with B, and if you get BC, then you seek for AC, and if not, then you need to add. So P comma Q, Q comma Q is there. There is no such element of the form A comma B, so no need to add. So it is 0 element only. So minimum number of elements that needs to be added, which is n1 plus n2 plus n3. Okay, and the equivalence relation is QQ and PP. Okay. So similar to this concept, let's change the set A to minus 1, 0, 2. Question is same. The relation is given to be minus 1, 0 and 0, 2. Again, the question is same. We have to find minimum number of elements to be added in R so that it becomes an equivalent relation, equivalence relation. So guys, what we will do, in order to get equivalence relation, we have to find minimum number of elements each for reflexive, which is n1, symmetric n2, minimum number of elements for transitive, which is n3, and numbers n1, n2 plus n3 is n minimum. These number of elements we need for this. Okay, so the solution goes like this. This set minus 1, 0 and 0 comma 2, clearly for reflexive relation minus 1 a type of elements are not present, so we need to add how many elements? So yes, 3 elements, minus 1, 0, 0, 2, 2. So n1 is what, guys? Number of elements that we have added to make it reflexive, it is 3. Now for symmetric relation, if we have minus 1, 0, AB is there, then BA should be there. It means 0 comma minus 1 should be there, which is not, so we need to add. Okay, so 0 comma minus 1 we need to add, 0 comma 2, so we need to add what? 2 comma 0, so 2 comma 0. Okay, so number of elements that we need to add for n2 is how many? Yes, two elements are added. For transitive, guys, if minus 1, 0, 0, 2 is there, AB, BC, so AC should be there. AC means what, guys? AC means minus 1, 2 should be there, so that we will add here. So that we have added here. So one element we need to add. Okay, and we need to understand that so this is RT, not RS. This is transitivity, guys. Okay, so we need to understand that what we added before here, they won't have any bearing on what we have added later here. Okay, because if we combine all of them, still it would be an equivalence that we will see. Okay, so that minus 0, minus 1, 2 comma 0, if you check for transitivity here, it will give 0, 0 and minus 1, minus 1, minus 1, 2. Okay, that would be present here itself, so it will automatically take care of transitivity. Okay, so I haven't included it here, so n3 is 1 only. Okay, so n3 is 1. So only one, so number of elements that we finally need to add to this are 3, 2 and 1. 3 plus 2 plus 1, 6 elements we need to add to make it equivalence, and you can recheck it here also. There won't be any elements missing. Okay, we can also do it by adding the elements from what we have got in reflexive to symmetric, and then adding all the elements that we have got from reflexive, symmetric, and then again trying to get number of elements for transitive. You will get the same. Okay, so I haven't added to make the calculation lesser, but that way also it can be done. It can be, we can get the same, we will get the same answer. Okay. Now if a relation a r1b, if and only if a is less than equal to b, where a b belongs to r square means a is also real number, b is also real number. The question is r1 equivalence relation? So yes, equivalence means the hint would be we need to check for all three, starting from reflexive, then symmetric, then transitive, and so on. If any one is failed, we won't go for checking the next. Let's take this. We'll go for testing for reflexive. So we will put b is equal to a less than equal to a would be true. So it is reflexive. So yes guys, reflexive relation is pass. Now we will test for symmetric. So if a is less than equal to b is true, what about b greater than equal to a? Sorry guys, this if a and b, if we interchange here, b less than equal to a b if we interchange, so you can, what we can say about this? So if you take 2 less than equal to 3, 3 less than equal to 2 won't correct. If this is correct, this won't be correct. So this is wrong. So it failed in symmetric. For symmetric, it won't be true. So we won't test for transitivity. Directly we will declare that it's not an equivalence relation, guys. So let's take an example, guys. A is a union of 10 sets A1 to A10, where any two sets has at least 4 elements common. Means if you take union of intersection of any two sets, let's say A2 and A3, they will have 4 elements common. This is the meaning of the first three statements. Now relation capital R A to A is defined such that A R B, if and only if A B belongs to AI square, means A and B are belonging to the same set from 1 to 10. Okay, means if it would be a part of the element is a set, and A comma B is a part of the relation if and only if both the sets, both the elements which are sets, they are belonging to the same set. Okay, AI. I can be any. I means, for example, if A belongs to, let's say, A belongs to A2, then B should also belongs to A2. That is the meaning of this statement, guys. Okay. So now question is this an equivalence relation? So how do we approach this? So we need to test, this is a straightforward, so we will directly test for whether it is reflexive, symmetric or transitive, A B to B B C to AC. That we will check one by one. So starting with reflexive, A R B, A B belongs to AI square. So if B is replaced by A, so A comma A would be element of AI square, which is possible. So it is reflexive. Okay. Now testing for symmetric. ARB is AB. They both belong to AI square. So B, interchanging them, still they will belong to what? They will belong to AI square only. The same set which A, B belong. So yes, it is symmetric. Now testing for transitive, the third part, ARB, BRC. Now if B belongs to AI, obviously A will also belongs to AI. So AB belongs to AI square. Now since B belongs to AI, C will also belongs to AI. So AB also, AB, BC belongs to AI. So obviously AC will also belongs to AI square. So symmetric transitive is proved. So hence the equivalence relation is proved, and yes, it is equivalent relation. In this example, let's see what it means. Let A is a set 3, 4, 5, 6, 3, 4, 5, 6 up to 35. Natural numbers are there, and an equivalence relation RE A to A is defined such that A comma B RE C comma D if and only if A by B is equal to C by D. Okay, guys, where A, B, C, D are numbers belonging to set A. So then number of ordered pairs C comma D we have to find out belonging to RE, that is the equivalence relation when A is equal to 2 and B is equal to 5. Okay, so how should we proceed with this, guys? What should be the hint to this question? So A by B equals to C by D they have given, and already it is given that it is an equivalent relation. And if you think, do we need to prove this? No, it's not required, but we can, just in case if you are curious about why it is an equivalent relation, we can put AB, because here one element is equal to an ordered pair. So AB we can put AA, CD we can put AA also. So that way we can prove for reflexive. Then for AB equals to AB, AB here, and CD we will replace by AB. So that way we can prove for reflexive, and then we can interchange AB, CD to prove for symmetric. Transitive also we can similarly prove. So that way it is an equivalent relation. So it is, since it is given in the question, there is no need to prove it. So guys, A by B equals to C by D is given. We will substitute A is equal to 2, and we'll substitute A is equal to 2 and B is equal to 5 equals to C by D. So what C and D can be? So we can think of this to be A as equal 2 by 5 as 2k by 5k, where k is some natural number or some number. So C can be assumed to be what, guys? C is a multiple of 2, D is a multiple of 5, k can be any number. Now since ABCD, it is given that ABCD belongs to A, so they are natural numbers only from 3 to 35. So proceeding with this, we will substitute the values from k. So if you substitute k is equal to 1, you will get CD. This is the ordered pair CD. So we need to find ordered pair CD. Okay, so that way we can proceed. Okay, so till how many values of k we can proceed? So we can check the upper limit, which is 35. So the value of D is greater than C. So as you can see, D, when you take k is equal to 2, D becomes 10, C is 4. So we have to check for D. Now that way, if you think k is equal to 7, for k is equal to 7, it will reach 35. Beyond that we cannot go, because if you go for 8, the value of D will exceed the values from the set A. So number of ordered pairs is how many, guys? So yes, it is 7. So that way we can do. Now in this single correct question, it is given that R is a relation satisfying X, R, Y is such that X, Y, they belong to set of natural numbers and x square plus 3xy minus 4y square is equal to 0. So natural numbers must satisfy this constraint, then it would be R. So the question, we need to select one option. The first option is, it is reflexive but not symmetric and transitive. RR means, I have written below here, it is reflexive, this is symmetric, this is transitive in short form. Second is equivalence. Third is R and S means reflexive and symmetric but not transitive, symmetric but not reflexive and transitive. So what should we do to solve this? What should be the hint for this? So yes, the hint is to factorize the quadratic and check for each relation. Think, either try to prove, but before that try to get a counter example which proves neither of them. Okay, now we will try to prove, factorize this, which is a quadratic in xy. 3xy is written like this, taken by x common and 4y. We got x minus y out, x plus 4y out. So either x is y or x is minus 4y. So x is replaced by y, so y comma y, and here also x is putting y as y, x we are representing as minus 4y. So the two possibilities, it's a relation if the ordered pair is of the form, either of the form y comma y or minus 4y comma y. So now we have to check for reflexive. So clearly reflexive, you can see y comma y exists for all natural number. Clearly, directly we can say it is a reflexive relation. For symmetric relation, y comma minus 4y, let's say y is equal to 1. So 1 comma minus 4 is an element. So the question arises, minus 4 comma 1 exists. So clearly minus 4 comma 1 doesn't exist, because if you take y is minus 4y would be 16. So minus 4y clearly doesn't exist. So using this counter example, it is not symmetric. And for the transitive y comma minus 4y, again we will take a counter example. We will take y1. So 1 comma minus 4 is an element of R. So y comma minus 4 again is an element of R. So minus 4 comma 16 becomes, so the question arises, is 1 comma 16 is an element? Clearly, if one is positive, another should be negative. So it cannot be equal to y comma minus 4y or y comma y. It doesn't fit in any of the given two factors. So this is not transitive. So the option that we can put, that we can mark correct is, it is reflexive but not symmetric and transitive. That is the option A. Let's see a question, guys. Let PS is power set of S 2, 3 to 17. So we are aware of the meaning of the power set. Now a relation R is defined on PS, the power set of S, A R B, if and only if A intersection B bar union B intersection A bar is equal to phi, where A comma B, they belong to P square S. Means A belongs to what? PS, and B also belongs to PS. We have to check is R equivalence. So now let's see the meaning of this, guys. A, B belongs to power set. What is the power set of S? So S 2, 3, 17 means PS is like this. 2, 3, 17, it is 2. This should be in curly brackets. 3, 5, 3, 7, 10, and so on. So many sets are there. Number of power sets can be so many. If there are n elements, number of elements are 2 to the power n. Okay, so A can be any. This can be A, this can be A, this can be B. Okay, this can be A or B, this can be B or A, anything. So these are, the meaning of this is AB belongs to P square S is this. Okay, so they are basically a set, a subsets from made from the set S, which is 2, 3, 4, 5, 6 till 17. Now the question is our equivalence. So what should be the hint to this, guys? So the hint is definitely this relation, which is crucial. We need to understand this relation, uh, which gives us relation between A set A and set B. So that is the hint. So hint is, if this is phi, A intersection B bar, union B intersection B, A bar is equal to phi. Now from Venn diagram of two sets and inside this, we know that this portion represents A intersection B bar, and this represents B intersection A bar. So if you take their union, definitely the intersection won't be phi, it would be like this on the left and this on the right. So this would be basically this whole thing, guys. Okay, represented by the shaded region area. So now they have given it to be phi. So if so, as we can see A and B, if they are any general sets with respect to universal set, it is not equal to phi, as we can see from the Venn diagram in general. So now what if this is phi, which is given in the question? What is the meaning? So it's quite clear that we need to make, since it is union, both must be null, this must be null, this must be null, so that their union is null, right? So that should be the relation, that will give us the relation between A and B. So this is, if this is phi, this has to be null, this has to be null, then only will get null. So A intersection B bar is null, B intersection A bar, since it's a symmetric relation, the possibility is when A is equal to B, and if you substitute A, how we can get, we can also think of taking this side and this side, so that this graph reduces, this area reduces. Here also this will take this side, so A and B are merging towards each other, so that this area is reducing, and it becomes 0 when A and B are equal. So when A and B are equal, substituting B as A here and here, A intersection A bar is phi, A again it is phi, so we are getting phi. So the relation between A and B is A and B are same. So A and B are same, so it redefines the relation between A and B is A comma B belonging to PA square, such that A is equal to B. Okay, so clearly if A and B are equal, if we interchange them reflexive directly, it is A B is equal to C is equal to A, it will be transitive also. So we can directly say that it is what, guys? It's an equivalent relation. In this example, we have to prove that if R is any relation ARB, if and only if 2A plus 3B is a multiple of 5, when A and B are natural numbers, A comma B belongs to n square, this we have to prove that this is an equivalence relation. Means 2A plus 3B, where A and B are natural numbers, we have to prove that this is an equivalence relation if this is a multiple of 5, where k1 is some another natural number. That is the meaning of this. So we have to prove that this is an equivalence relation. So the hint means it is understanding the problem that will pave the approach towards solving it. So if we assume 3a plus 2a plus 3b as 5k1, 2a plus 3b is equivalent to a comma b. Okay, so then we have to think of proving three things. One is reflexivity, means a comma a. First, we have to prove that it is a multiple of 5. We can directly see that 2a plus 3a 5a is a multiple of 5. Second, symmetric means b 2b plus 3a. We are interchanging a and b here. A is replaced by b is replaced by a. So if ab exists, we have to prove that ba also exists, and it is what? It is also a multiple of 5. Third is transitive. That is, if a comma b means 2a plus 3b is 5k1 is true, then, and b comma c, which is 2b plus 3c is equal to 5k2, which is another multiple of 5k2. Let's say if these two are true, then we have to prove that a comma c should be a multiple of what? A comma c should be multiple of 5. A comma c, 2a plus 3c multiple of 5. That we have to prove. So the solution, the first reflexive, replacing b by a, so it is a comma a, which is 2a plus 3a, 5a. A is a natural number, so obviously it's a multiple of 5. For symmetricity, to prove that this is symmetric relation, if a comma b, that is if 2a plus 3b is 5k1 is exists, if it is true, then we have to prove that if we interchange a and b, that is b comma a, which means 2b plus 3a, we have to prove that this is a multiple of 5. So what we will do, we will assume 2a plus 3b as 5k1 and substitute a from this in this. We will get the value of a here and we will substitute it here and try to prove this whole expression to be a multiple of 5. That would be our approach. So following that, the next step, a we got, 2a is this, so a is 5k1 minus 3b by 2. Let's say this is first. Now b comma a, as I said, we will substitute a here, 5k1 minus 3b by 2, taking LCM, 2b becomes 4b, 3 is multiplied to this bracket, so which becomes what, guys? 4b minus 9b becomes 5 minus 5b. Okay, and this is 3 5s are, this is 15, 3 into 5, this is 15k1. So now taking 5 out and then writing 3k1 as 2a plus 3b minus 2k1. From this first equation, 2a plus 3b is equal to 5k1, minus b is as it is. So 3b minus b is 2b, 2a is as it is, minus 2k1 is as it is, so 2 comes out and 2 we can cancel out with this. So we are left with 5 times, let's say it is k2, so it's a multiple of 5 we have proved. So a comma b, then we are getting b comma a is true, so this is symmetric, we have proved. For transitive, as we have seen in the hint, if AB, BC, then AC is true, means we have to prove that 2A plus 3C is a multiple of 5 if these two equations are multiple of 5. So adding first and second equation, so first is this, second is this, adding these two, we will get this equals to 5, taking 5 common, 5k1 plus k2. Now taking this term, 5 be on right hand side, 5 we will take common, so we were left with minus b here. So it's a multiple of 5 we have proved, but we need to prove that a comma c, okay, so that we have proved it, okay. So a comma c is proved, c comma a is also true, okay. A b b c, so AC is true. This is what we are trying to prove. Assuming AB, BC, AC is proved to be true, so transitive is proved. So the relationship, the equivalence relation is proved, guys. Okay.